So waves are all around us in sound, light, water and, well, even that. What's that? It's a microwave. So let's look at which ones are progressive waves and which ones are standing waves. Firstly, I'm going to recap on what I mean by the term wave. A wave is simply a disturbance that transfers energy from one place to another without transferring any matter. In physics, we have two kinds of wave. One is transverse, where the particles of the medium oscillate in a direction perpendicular to the direction the energy is moving, or they can be longitudinal, where the particles oscillate or vibrate along the same direction as the energy transfer, for example, sound. Now we've got that clear, let's move on to the two main types of wave we'll be dealing with today: progressive waves and standing waves. Progressive waves, sometimes called travelling waves, are waves that move through a medium, transferring energy from one place to another. Imagine flicking a rope. You put the energy in one end, the energy travels along the rope and is transferred to the other end of the rope. That's a progressive wave. With a progressive wave, every particle along the wave moves, going through one complete oscillation or one complete cycle. There's a continuous forward motion of energy. Now, standing waves are quite different. Unlike progressive waves, standing waves don't seem to travel. Instead, they appear to stand still. So what's going on? A standing wave occurs when two waves of the same frequency and amplitude moving in opposite directions interfere with each other. The result? A wave that looks like it's not moving at all. But this does not mean that no energy is involved. It clearly is. But the energy is confined within the wave pattern. If you look closely at a standing wave, you'll see there's parts that aren't moving at all. They're called the nodes. There are other parts of the wave that have a maximum amplitude, and they're called the antinodes. Now let's compare these two waves side by side so we can clearly see their differences. Firstly, movement of energy. In a progressive wave, energy is transferred from one point to another. The wave physically travels through the medium. You can see that each particle of the wave moves as the wave passes, transferring energy forwards. But in a standing wave, the energy is not transferred through the medium. It's confined between the nodes and the antinodes. 2. Movement of particles. In progressive waves, every particle vibrates and moves as the wave passes through. Each point of the wave goes through a complete cycle, going from a positive maximum amplitude to a maximum negative amplitude, and then back again. But with standing waves, only certain points move. The nodes stay fixed while the antinodes experience the maximum movement. 3. Wavelength and frequency. Both progressive waves and standing waves have wavelength and frequency, but they behave differently. For progressive waves, the wavelength is a distance between two consecutive points that are in phase, like two crests or two troughs, and the wave moves along with this constant wavelength. With standing waves, the wavelength is dependent on the distance between the nodes and the antinodes, and you can only achieve certain values of standing waves. This is why they're linked to the idea of resonance. Now we've got some understanding of progressive waves and standing waves, let's have a look and see where we can find them in the real world. Progressive waves are everywhere. Think of ocean waves where energy is transferred through water, or sound waves where energy is transferred through the air or some other medium. You've probably figured out that light waves are also progressive waves. But standing waves are also pretty common. You can find them in musical instruments such as guitars or violins. When you pluck a guitar string, a wave set up that's reflected from the two fixed ends comes back and forms a standing wave, and that standing wave produces the note. Microwave ovens also use standing electromagnetic waves to cook your food. Before I briefly mention harmonics and go through the maths of standing waves, can I just mention that there's some questions to download for you completely for free, along with worked answers, all available on my website, and there's a link in the description below. To enable me to continue to produce all these free resources, it would be really helpful if you could like and subscribe. I also love to read your comments. When standing waves are set up, it's usually easy to determine if there's going to be a node or an antinode at each end. For example, a guitar string's fixed at both ends, so there must be a node at each end. In an instrument that has a pipe that's closed at one end and open at the other end, there must be a node at the closed end and an antinode at the open end where the particles can move. Using this information, we can determine what wavelengths a standing wave can be set up. Let's take a look again at these two examples. For a guitar string where there's a node at either end, you can set up a standing wave where the length of the string is the same as half a wavelength. That would mean that the wavelength of the standing wave would be twice the length of the string. With a pipe that's open at one end, you can actually set up a standing wave where the length of the pipe is quarter of a wavelength. So one wavelength would be 4 times the length of the pipe. In both these examples where we're setting up the waves with the longest possible wavelength, we call them the fundamental or the first harmonic. For a guitar string with a node at each end, you can then get subsequent harmonics as shown by this equation, where L is the length of the string. For a pipe that's open at one end, you can then get further harmonics as shown by these expressions. Harmonics other than the first harmonic aren't really covered by a lot of A-level syllabuses, but I thought it was well worth a mention. The frequency of a standing wave in a guitar string depends upon the length of the guitar string, the tension in the guitar string, T, and also how heavy the guitar string is. We describe this sort of heaviness as the mass per unit length, and we give that the symbol mu. The equation that gives us the frequency of the first harmonic, or the fundamental, is F equals 1 over 2L root T, the tension, over mu, the mass per unit length. On this Fender Stratocaster, the standard length of the string is 648 millimeters. The first harmonic frequency for the low E string is 82.41 Hz. The mass per unit length of the string is 10.3 grams per meter. What's the tension required for the string to be in tune? Well, let's substitute our numbers into the equation. The frequency is 82.41. We get 1 over 2 times the length, which is 0.648 meters, times the root of the tension over the mass per unit length, which is T over 0.0103. We can rearrange this a little, and then we can square both sides. Rearranging and sticking the numbers into the calculator, we get 108.1 squared times 0.0103 equals T, which equals 120 newtons. That's like hanging a 12 kilogram mass on the E string. You can see why the guitar neck needs to be so strong. Hopefully you found this useful, and you might want to watch this.